Greetings AP Calculus students, and welcome to Section 2.3 Continuity. In Section 2.3, this is what we're going to be talking about. We're going to identify the intervals upon which a given function is continuous and understand what it means for a function to be continuous. We are going to remove any removable discontinuities by extending or modifying a function. And then lastly, we're going to apply the intermediate value theorem as well as the properties of algebraic combinations of continuous functions. So this is a pretty ambitious list. Let's get started. First, we have a definition, the limit definition of continuity at an interior point. So this is what it means when we say that a function is continuous at an interior point. And by interior point, I mean if we're looking at our function on some interval from a to b, I'm not looking at endpoints a and b. I'm looking somewhere in between them on the interior of that interval. So here is our definition. A function f is continuous at c, at that interior point c, as long as the following things are true. First, f of c has to be defined. Second, the limit as x approaches c of our function has to exist, which means from both sides, from the left and the right. And then lastly, that limit of f of x at c has to be equal to the function value at c. So a more cheesy definition, or a more simple definition of what continuity means, is a function that you can draw without lifting up your pencil. So there's our little mouse, our little cheesy guy. Okay, more definitions. Okay, we talked about what it means to be continuous at an interior point. Now we're going to talk about endpoints. So if we're looking at the left endpoint of an interval, a function would be continuous at a left endpoint as long as we approach that endpoint from the right. So if it's a left endpoint, we need to be coming in from the right side of that. We would need that limit to equal f of a. Similarly, to be continuous at a right endpoint, we would need the limit of that endpoint as we approach it from the left side to equal f of a, and then our function is going to be continuous at that right endpoint. Okay, so take a couple of minutes and sketch this graph in your notes. It's not super important here that you actually graph the piecewise function that gives us this graph, but just go ahead and take a couple of minutes and sketch this graph, and then we're going to answer some questions about where this graph is continuous at what points in this graph from 0 to 4. So get the graph sketched, and then in the next slide we're going to talk about where it may be continuous. Okay, so where is f of x continuous at an interior point, at a left or a right endpoint, or where might it be discontinuous and why would it be discontinuous? So the first point we're going to look at is at x equals 0. So at x equals 0, the question is, would you say that the function is continuous there at an interior point, at an endpoint, or it's not continuous? Well, at x equals 0, we're continuous at a left endpoint because the limit as x approaches 0 is 1, and f of 0 is 1. And as we approach 0, of course, we're approaching from the right, because our function isn't defined over here. So right there, we're continuous at a left endpoint. Let's see, letter B, at x equals 1. So at x equals 1, we are not continuous. So we would say it's discontinuous, and the reason is because the limit as x approaches 1 doesn't exist. We have a different left-hand limit than we have a right-hand limit, which means the limit as x approaches 1 does not exist. Therefore, our function cannot be continuous at 1. Okay, at x equals 2, well, let's see, our limit as x approaches 2 does exist, because whether we approach it here from the left or here from the right, our limit is 1. However, f of 2 is equal to 2. So if the limit is not equal to the function value, it's discontinuous. At x equals 3, let's see, the limit as we approach 3 from the left side and from the right side, that limit exists, and also f of 3 is the same as that limit, so it's continuous at an interior point. And lastly, at x equals 4, well, the limit as we approach from the left side of 4 is equal to f of 4. So that is criteria for being continuous at that right endpoint where x equals 4. Okay, different types of discontinuity that we're going to encounter. First, when we have a hole in the graph, it's called a removable discontinuity. Next is when your function takes a big jump, and that's called a jump discontinuity. Our function we could have running off to infinity or negative infinity, and that's called an infinite discontinuity. And then this last one is called an oscillating discontinuity. You can see as we approach 0 here, our function just keeps going up and down and up and down and up and down. So it's not continuous because we don't have a limit that exists. When it just keeps going up and down and up and down, our limit does not exist. So we have what's called an oscillating discontinuity there. Okay, so one of the most common types of discontinuities we're going to see is a removable discontinuity. And when we have a removable discontinuity, we have to know how do we remove it. So let's start by looking at this function. F of x is equal to x cubed minus 7x minus 6 divided by x squared minus 9. So this is how we remove a discontinuity that is removable. First, we want to factor out the numerator and the denominator and see what our domain is. So we need to factor this numerator, x cubed minus 7x minus 6, and I'm going to use the Inspire to help me do that. So get your Inspire out, pause the video if you need to. And okay, here's my Inspire. So I want to factor an expression, and our Inspire will do that for us. So to do that, we're going to go to Menu, and we need to, oh, actually, on the home screen, let me make sure I'm in a calculator here first. Okay. So now I'm going to go to Menu, and factoring is an algebra thing to do. So we're going to go to our algebra menu, and selection number 2 says factor. So all we have to do is enter that expression, and that expression was x cubed minus 7x minus 6. And we hit enter, and voila. Our lovely Inspire will factor that into the quantity x minus 3 times the quantity x plus 1 times the quantity x plus 2. So there we go. There is our factored form. X minus 3 times x plus 1 times x plus 2, and then our denominator, of course, x squared minus 9 factors into x plus 3 and x minus 3. So our domain, we know we can't have division by 0, so our domain is going to be all of our x values except 3 and negative 3. So now we're going to identify what we have as removable and non-removable discontinuities. Those 2 points, the 3 and the negative 3, they're discontinuity points, and some of them may be removable and some of them may not be. Well, the removable ones are the ones that when we factor would cancel out. So that means right here we're going to get a removable discontinuity from this. So the value of x equals 3 would be removable, but x equals negative 3 from this factor, I can't cancel that out with anything. So that's going to remain being a non-removable discontinuity at negative 3. Okay, so once we've established what we have is removable and not removable, we're going to remove those. And the way we do that is we find what is the value of the function at that removable discontinuity. So we're going to look at this function, and we are going to cancel the two factors that are the same, and then that's at x equals 3. We're going to plug 3 into the remainder of the function. So f of 3, when we use our f function being the x plus 1 times the x plus 2 divided by the x plus 3, so if we plug 3 into that function, we're going to get 26 or 10/3. So we've just now figured out what the function value is at our removable discontinuity. Our f of 3 is 10/3. And to completely remove that, we're going to rewrite and extend our original function by defining the function at that removable discontinuity point. So we're going to call our new function g of x, and it's going to be our original f of x function, plus at our removable discontinuity at x equals 3, we're going to define the function to be that function value of 10/3. So now we have removed all of our removable discontinuities. That doesn't mean that this function is now continuous everywhere. It's not. We still have our non-removable discontinuity point at -3. So if you were to graph this function, this new g of x function, you would see that we still have a point of discontinuity at x equals -3, but we have removed the discontinuity at x equals 3 by adding that into our piecewise function. Okay, we're going to discuss what does it mean to be continuous on an interval versus the entire function being continuous. So to be continuous on an interval, that's actually a little bit more strict. To be continuous on an interval, the function has to be continuous everywhere on that interval. Every single point in that interval, our function has to be continuous in order for that function to be considered being continuous on that interval. However, for it just to be a continuous function, it has to be continuous everywhere in the domain. So what that means is sometimes we have a continuous function that's not continuous in a particular interval, which kind of might seem counterintuitive, but when we look at an example, you're going to see what exactly that means. So the example we're going to consider is f of x equals 1 over x. So we're looking to see, is it continuous on these intervals versus is the function itself continuous? So on the interval from -2 to 2 inclusive, that means everywhere between -2 and 2 is this function continuous. Well, that answer is going to be no, because this function is not continuous at x equals 0. When x equals 0, we have division by 0, and we know that means we're going to have an infinite discontinuity there. We know this function goes off to infinity or negative infinity as we approach 0. So that function, 1 over x, is not continuous in this interval because it's not continuous at 0. However, is the function itself considered to be continuous? Yes, it is, because to be a continuous function, it must be continuous everywhere in the domain. Well, in the domain of this, 0 is not included in the domain, so we kind of throw 0 out, and we say, okay, it's continuous everywhere except for 0. So that means we have a continuous function. Okay, let's look at our next interval here at 5 to 10. Well, anywhere x is in between 5 and 10 inclusive, we're going to be continuous. We don't have any bad things happening in between x equals 5 and x equals 10. So it is continuous on that interval, and it of course is also a continuous function. And let's look at our last interval here, -1 to 1. Well, -1 to 1 is similar to -2 to 2. It's got a point of discontinuity for this function because, again, we're not continuous at 0, which is included in that interval. So the function is not continuous on the interval -1 to 1. But we do still say it's a continuous function because the place it's not continuous is not in the function's domain. So that's difference of continuous on an interval versus just being a continuous function.